Okay, maybe we can get started today. So, good morning and welcome everyone. This is a talk in the VCO series, which is the Virtual Consulting Office organized by iGuide, which is the Institution for Geospatial Understanding through an Integrative Discovery Environment. My name is Anand Padmanabhan, and I'm a research associate professor at the Department of Geography and Geographic Information Science at University of Illinois. And I am also serving as a managing director for this iGuide project. So today, we are very honored to have Zhe Zhang, Dr. Zhe Zhang from uh, Texas A&M University, and she's with the Department of Geography there and an assistant professor there. Jo has been my colleague for a long time, and I know Jo quite well. And I have kept track of her research, and she has been phenomenal researcher. And she is working in the intersection of cyber infrastructure, cyber GIS, decision making under spatial uncertainty, and geospatial data science. She is also leading kind of the cyber GIS and decision support system research initiative at the UCGIS, which is the University Consortium for Geographic Information Sciences. And she is really well published in a number of top GIS journals, as well as she is supported by many federal agencies like NSF, DOT, NOAA, etc., and NASA, etc. And she also is a recipient of the NSF Career Award, the prestigious award there, and she is also leading a NSF cyber training project. There are a lot of things Jo has accomplished in a short time. So we'll be hearing from Jo today on spatial decision support system in the era of big data and disaster science. So welcome, Jo, and thank you for agreeing to present as part of the VCO series.
Thank you, Anand. So I'm so honored to be here, and thank you for the invitation. And thank you for the so good introduction about me. So I think I don't need to actually go through these slides anymore. Your introduction is already covered all the aspects. Yeah. So I'm Jill. I'm assistant professor in Department of Geography at Texas A&M. So before I worked with Anand at the Cyber GIS Center for almost 2 years. So it's so nice to see you, see my old colleagues. And I have been actively also contributing to the GIS science communities. So I also hold several affiliate positions at different departments at Texas A&M, and also at the Gulf of Mexico coastal ocean observing systems. So my research is focused on developing intelligent spatial decision support systems using a cyber infrastructure-enabled GLAI to help to build coastal resilience and sustainability. So as we know, nowadays, our world has grown more urban and more integrated, and with a greater of people at risk than before. So my research is really heavily focused on coastal, because the coastal cities are at high risk from many disasters, and also from the sea level rise, for example. And while the densely populated urban centers also face challenges such as air pollution, urban heat island, and also the impact of flooding. So therefore, the decision making is so important for building the community resilience. Why? So because the consequences of effective or ineffective decision making can have a huge impact on human lives and property and overall recovery process. So the bad decision can cause really big consequences, like for example, loss of lives. Therefore, we need to have a intelligent decision support system to be developed to help us to build resilience. So by the way, then what is the intelligent spatial decision support systems? So as you can see from this figure, so first of all, it is a computer-based system that requires the computing power to analyze extensive geographic data, right? So we need to have computing power to analyze data. And secondly, the decision support system should incorporate an intelligent components. So what's that mean? What's the intelligent components? It means to capable of understanding, to capture the understanding of the decision makers' goals and objectives. So we need to understand humanities, right? What the decision makers are thinking. So therefore, these knowledge acquisition techniques are important in this field. So finally, we also need to have a decision-making capabilities. So that serve as the brain of the decision support system. That refers to all the mathematical GL/AI models. And we also need to handle the data because the geospatial big data now plays important role. We need to learn how to handle the data, share the data, and how to analyze data. So there is a lot of effort now going on to how to make the spatial data fair, right? So and during the past 10 years, so my research has been focused on almost all aspects of these 4 core elements to develop the intelligent decision support systems. And I will give you some examples later on. So let's first talk about the knowledge acquisition. So as a geographer, we all know there's a big research on space and place. So in geography theory, we often talk about space and place, right? So the place refers to the geometric concept of the location of objects and activities or phenomena. But the place is more subjective concept that involves the human experience to a specific location, right? And the spatial acquisition or cognitive techniques have been often used to collect human knowledge about the geographical world. So in my research, I'm more focused on these 2 research questions. So first of all, how people come to understand, represent, and behave within their spatial environments. And second, how to integrate human knowledge into a geospatial modeling approach to support intelligent decision-making. So I will show this with some of my previous work. So the first one, I have I would say like during my PhD and then first year of postdoc work, I have been continuing working on the mixed methods. And this paper was published in the early years by the IGGS journal. So the data used for this work is the Helsinki building and population register data. So we know in each building how many total amount of children and population live in this building. So we know that information. But the motivation of this work is to address the vagueness in spatial cognition. So meaning in the emergency situation, the emergency managers, they make decisions really based on their expertise or the experience, how well this emergency manager knows the area where he or she is like managing. They do not have time to look at maps or analyze data. But there is a vagueness in spatial cognition, meaning that, for example, there are 2 buildings. The emergency manager has to evacuate people from the flooding, for example. So if one building has 100 people and 10 children, and another building has 80 people but 15 children, so which building this emergency manager should go first? Can they say? So can we say that the building A is more vulnerable than building B because it just have a higher amount of people living in? So no, because there's no crisp boundary. We cannot say 100 people is more vulnerable than a building that has 99 people. So there is no crisp boundary, right? So it's vague in that in terms of the vulnerability. So instead of using a crisped models, I have developed the fuzzy model, and I also conducted a survey and interview and designed different kind of questions to ask the emergency managers their risk perception. And so instead of say building A is absolutely vulnerable in case of the flooding, we say we developed a degree of membership functions, is meaning we say that, okay, if this building A has total 100 people and then 10 of them are children, we say this building is more likely, measured by the degree of membership function, more likely to be vulnerable than the building B. And we also develop fuzzy rules. So for example, if the building A has a high amount of people and building B has and a high amount of children living, and then this building is more like a Z, which is then this vulnerability is high. So I conducted the interview and surveys to design this membership function. So all the corner points, all the functions, the value of the function was actually derived, those numbers were derived from the survey. And after that, we are able to map the vulnerability on the map, as you can see in the right side. So the red and purple area represent the places is more likely to have a high population and also high amount of kids living. So the emergency manager should go to those areas to rescue people. And this is the second application. As we know that volunteer geographic information, such as social media data, has been often used to map the place. And in this work, I used the Twitter data collected from January to April in year 2020. It's about 80 million tweets. To map depressive symptoms of people caused by COVID-19. So as you know, during COVID-19, people have to cancel their plans and stay at home. So there was a lot of depression, or it's not nice. So there's many people with has a mental health issues. So we aim to develop. In this work we developed this map to show the depressive symptoms caused by COVID-19 at spatial temporal scale. And we developed a novel algorithm called the Core EXQ9 that combines a correlation explanation learning algorithm with a clinical depression detection lexicon to detect the COVID-19 related stress symptoms. So for you who do not know about the clinical depression detection lexicon, so if you have a depression, you normally go to hospital, and then the doctor will give you some survey you have to fill in to describe your feelings. And then based on that, actually the hospital, they develop the lexicon to evaluate the patient's stress level in 9 categories. So the category 1 is the very light, but category 9 is the like a more serious, if you have more serious depression. That maybe need a medication. So the darker color on the map shows the higher level of depression caused by COVID-19. And we were also able to detect the topic changes at the spatial temporal scale. So for example, from January to April, most of the regions have a low to medium stress level values. And the topics are related to, for example, Chinese doctor Wen Liangli, and symptoms of the COVID-19 like sneezing or coughing. And from the end of January, a few hotspots appears in some major cities, such as San Francisco or Los Angeles, with a topic related to like a mistakenly released patient, vaccination, and also the amount of death that has been in China. So we also develop a dashboard to visualize these results online so people can observe. And the third example is related to advanced visualization techniques. So we all know about augmented reality. So this is the platform or the technology which we can visualize the point of interest data. And so the motivation of this work is that I was traveling in Seattle, I think, and that was my first time. I didn't know the city so well, and I was in the shopping center in the evening, but I'm a little bit worried if there's a crime around or should I go back to hotel. So I start to look for the website and see the like Seattle crime rate, or I think during that time, not sure, it was also pandemic. So I want to find all the information about the neighborhood, but I noticed that it was very hard to find all the information in one page. It took me a long time. So then it's come to idea like why not we develop the augmented reality to help people to navigate to their location, but at the same time to improve the situational awareness. So for this work, I use the Twitter data. So with Twitter data, we can map people's emotions, like if people feel happy or fear or angry about this place, what they have tweeted about this place. We also use census data, to see the social vulnerability, poverty, and those indicators. And we also have the point of interest data that can navigate you to the shop. So for example, here to this Burlington shop is about 10 meters. And so here, if I click on this, you can see this actually visualize all the information in one platform, in the augmented reality platform, to tell about the neighborhood that you are currently at. And of course, the key innovation on this work is to design the advanced cyber infrastructure to tackle the interoperability and latency issues. So I will talk about that later in my later slide. So let's come to the second part, the decision-making capabilities. So in the early years, before the AI become popular, multi-criteria decision analysis has been widely used in spatial decision support systems. And I have published several papers, I think at IGGS and International Journal of Digital Earth, which we use the multi-criteria decision analysis for developing the disaster-related decision support systems. And later with rapid development of the geospatial big data, so I moved my interest towards the cyber infrastructure and cyber GS. So I have organized a special issue in year 2021 on the cyber infrastructure and the spatial decision support systems. And I want to talk a little bit more about the recent work related to MCDM. So this is the paper we just got published a couple of months ago. It's very new. So it's published on Annals of the AAG journal. This is not directly related to disaster, but it's definitely related to coastal and sustainability and climate change. And this work has been funded by NSF Convergence Accelerator Network Blue Economy program. So the motivation of this work is, the US government has announced a plan in year 2022 to generate about 30 gigawatts of energy, like offshore energy, by year 2030. So they're gonna build a huge amount of offshore wind energy platform in the coastal area. So however, the building this offshore wind energy will have a significant negative environmental impacts on fisheries and also coastal environments. And there's not much study has been done to investigate this conflict. So my motivation is that are there overlaps or conflicts between expected fishing efforts and human activities like fishing or aquaculture? And can we find spatial solutions for balance the trade-offs between them? So the data used for this work is the California Department of Fish and Wildlife data, and the National Renewable Energy Laboratory data, and National Transportation Atlas database, and also a USGS data set. So in this work, we have developed three decision-making models. It's a weighted aggregated sum product one model. It's and then the analytics hierarchy process model, AHP, and top six model is a technique for order of preference by similarity to ideal solution. So those are the multi-criteria decision models. And we have used the following criteria to evaluate the suitability of building the offshore wind at certain location. So that's the wind speed. So of course, we want to build the offshore wind platform at a place which has a high amount of wind, right? The wind speed in the history and the distance to shorelines. You cannot build too close to shoreline, and the distance to military base, and distance to the protected area. And also the landing data. So the landing data refers to the historical fishery production, like how much fish has been produced during that area. So the blue polygon on the map represent existing core area. So in California, they have already planned those three core area that they want to build the offshore wind. So we have simulated 8,000 weight combination to see which combination these three core areas will receive the biggest suitability score. And after those simulations, and we found that among all weight combination as input, so the higher focus on non-fishery criteria. So we just ignore the landing data. Then is highly positively correlated with a higher suitability score. So it means that these core areas now, these three core areas, when they decide on those three core areas, they have not really considered the fishery or environmental impact. So here's has more detailed information. In the left side, this refers to the Eureka core area. And without considering the landing data, the fish production data, this area is highly suitable. It has high wind speed and the distance and everything's perfect. But after we add into the fishery data, and this area is no more actually suitable for building the offshore wind. So it's meaning if you put offshore wind here, it's gonna have a significant impact on fisheries. So with the rapid development of GeoAI, artificial intelligence, we also have a lot of work done in that area. And one of this is heavily focused on flood mapping. And this work is funded by NOAA Sea Grants. And the study area is Houston. It's very close to my home, 1.5 hour drive. So as we know, Houston has experienced almost every year heavy flooding and the rainfall. So we receive about 45 inches of rainfall in almost 106 days annually. And of course, we have a gauge data. We have about 177 gauge stations in Harris County, but they are in different shapes. And sometimes it's difficult to read. Sometimes they put those gauge under the bridge, and it's very easily to get inundated. And also the most importantly is that we have only 177 gauge stations. So how about the places that we do not have, right? So it's not on the street level. But on the other hand, we have about 950 million of stop signs in the US states. And in the United States, all the stop signs, they are in the same length, same shape. So I came up with the idea that how about we use stop sign as an intelligent sensor to measure the flood depth. So how to do that? We have leveraged citizen science. So the motivation of this work is how can communities be involved in the effort to collect, exchange, and analyze disaster data in order to reduce the disaster impacts. So we have developed the citizen science and computer vision algorithm, meaning we partner with the nonprofits and communities. So they will take a photo when there's a stop sign in their neighborhood has got flooded. And we also collected Google imageries and we pair those photos. And because, as I said, in the United States, all the stop signs have the same shape and same length. So we can easily, using computer vision, we can easily find out how much the pole of the stop sign has been inundated. And then we can map that on the web app. So my research group, my student had developed this web app called Blue Pics. So user can upload photos, the flooded stop sign photos, and we have a computer vision algorithm embedded behind this app to calculate the flood depth. So this is the blue dot, this blue marker. If you click on this blue marker, it's gonna show you this flooded stop sign. And it's also gonna show you the flood depth. So here, I think the flood depth is about 29 inches. So if we have enough paired photo, we can actually map the flood situation at every street. So once we know the flood information, like if we know where it has been flooded, so the next step is to help evacuation, right? To have people stay safe, to avoid flooded area. And this is a new paper we just published a couple of months ago at the International Journal of Geographical Information Science. So we developed this reinforcement learning-based routing algorithm for large street networks to help community to evacuate and to avoid flooded area. And the motivation of this work is that we all know these traditional routing algorithms, but the traditional methods like A** are often based on pre-trained rules and not able to adapt to a real-time situation. And they also suffer from scalability issues when dealing with a large amount of street network nodes. And it also lacks of the ability to deal with diverse data source. So for example, if some place is closed or if you have multiple factors considering when you do routing, and those traditional algorithms might have drawbacks. So our work will tackle those challenges. And we use the OpenStreetMap data to map the street network. And we use the Houston and New York transportation data, OpenStreetMap, and 311 data and the gauge data. So the 311 data is to report instance, right? And the gauge data is used to measure the flood depth. So those blue dots, for example, those are the gauge data, and those blue dots represent the flooded area. So we try to avoid those blue dots when we do routing. So for you who do not know reinforcement learning, so I can give a little bit background. Reinforcement learning is a machine learning algorithm, so in which the agents learn to make decisions by interacting with the environments. And the agents receive feedback in the form of reward or punishments when it's navigate to the environments. So in order to set up the training environments, we have 3 steps. First is the state. It refers to the neighborhood of the agent can see. So it's just to map the connectivity of the road and the neighborhood of the agents. The second is the action. So meaning this agent can go forward or turn left or turn right. It depends on the current location this agent is now sitting. And then the reward. So the reward is like when the agent start moving. For example, if this agent touched the blue points, of course, it's going to get a negative. It's going to get punishment. But if it's doing well, then it's going to get a reward. So we have a so the key innovation was to develop a novel award function using a policy gradient optimization methods. And these optimization methods can imitate experts' decisions to support agent navigate in a large road network. So in this work, we have about 80,000 of nodes. And as you can see, this in the right side of the figure, it shows our starting points as yellow dots and destination as green points. And the blue points are the flat points. And then the path, which colored the red, is using our reinforcement learning algorithm. And to validate our methods, we also compare this with a traditional routing algorithm. In the left side, the blue line is the traditional algorithm, and then the red one is our reinforcement learning based. As you can see, our algorithm, our methods is outperform those traditional methods. It can help the agents or help the people to stay further away from the flooded point. So in the y-axis is the distance to the flooded points. So we are actually further away from those flooded points. So now come to finally the data handling part. So geographic data is very important, and there are so many data sharing platforms available to share geographic data. And for example, NASA and USGS. And since I'm the council member of the Gulf of Mexico Ocean Observing System, so they, GGOOS is called GGOOS. GGOOS actually share all the ocean observation data. So they have a data sharing platform. So in the right side, this picture shows a user can enter the keywords, and then it's gonna return as a table. So the GGOOS data is in tabular format. But as you can see, it's not very user-friendly because it provides limited information about the data product. It's basically just gonna return you a table and tell you the download link and etc. and metadata. But it does not tell you much about the data and also the relationship with other data product. So now the generative AI and the large language model is very popular. And we have the idea of developing a question answering system using a generative AI and large language models to help users to better understand the data product and also help them to better find suitable data. So in this case, we applied a modified bidirectional and auto-regressive transformer. It's a BART model as the base language model to understand the text. And then after that, we modify the BART language model that follows a standard sequence-to-sequence transformer architecture. And then we load this pre-trained BART model with about 400 million parameters on SQL synthesis to initialize the fine-tuning model weights. And after that, the pre-trained language model is tuned with a multi-round of tuning methods with various data set, including the Wikipedia question answering data set, and also metadata question answering data set. So we use, of course, we use GGOO's data, which is in tabular format. We also use Wiki and other language, knowledge-based data. So finally, we fine-tune the model with the optimization algorithms, and by updating the model's parameters to minimize cross-entropy loss functions, which used to measure the difference between the model's prediction and the true label. So we do measure the quality, the accuracy of our model. So if it's really give the correct answer, and this work has trained on the GPU machines, and with about 20,000 steps. So I will show you how this look like. So here is an example. For example, if user enter a question, so what's the date range for data for IU station 42856, is our meta QA gonna give you the answer, so the dates of that. And we also compared with other models like OmniTab or TabX, and it shows that our model outperforms other models, and with a reasonable good accuracy. So with this, meta QA is really can help help the users to better navigate or better understand the data they are looking for. Finally, we have the cyber infrastructure part, the computing system. So I have several projects funded by National Science Foundation Office of Advanced Cyber Infrastructure. So I'm both also a co-PI in the hardware side. So for example, in Texas A&M, we are building a GPU-enabled supercomputer called Faster and Access. And I also currently working on cyber training projects. And I just had a workshop, organized a workshop at the AAG annual meeting. So now I'm going to show you some of the work that behind those fancy web apps. So you know this, for example, for the Blue Pix app, you see it's very nice. User can click on the markers, and then the app gonna show you the flooded air, the flood depth, but it's not very easy to develop such app. So there is a cyber infrastructure design behind it, how to design the front end, GL middleware, and then the back end. And then we also, in addition to software, my research lab also have our own hardware. We also have a high performance cluster, which designed using a Kubernetes Kubernetes technology. And this is the cyber infrastructure design for the AR app. I introduced a little bit when I introduced this application. So in the model training part, we have all the social media data, point of interest data, all integrated into a high performance computing cluster. And then in the middleware, we have different database to measure, and then we have servers. And then in the front, we have the AR, which has which shows the device location, camera positions, and time, where user can use AR to navigate to different neighborhood. And this is the cyber infrastructure design for the routing algorithm. Again, this is hosted in the Kubernetes cluster. And it has different worker and driver nodes. They have different tasks, and we have also GL middleware. And we also have like a etcd. It's like a key value store used for sharing the configuration and service discoveries in the distributed system. We have different, packages like technology installed in our cluster to make this routing app working. In addition to my research project, I also have several funded education projects. So one was funded National Geographic Society. So we are building a Texas Youth Geography network for helping high school teachers and the students to advance the AP Human Geography and AP Environmental Science Studies. And they have developed over almost 17 story maps for the AP Environmental Science and AP Human Geography classes. So the high school teachers can use our story maps in their classroom. And I also have a Texas Department of State Health Services project. And I have organized a lot of youth outreach and education activities. So the first picture shows the high school poster competition I organized at UCGS Symposium year 2022. And then these two pictures, I also organized the Girls Exploring Math and Science camp at the Houston Museum of Natural Science. So finally, I want to introduce our current ongoing project called Cyber Training. Dr. Shaowen Wang and from UIUC, Department of Geography and Geographic Information Science is the co-PI, and also we have Dr. Honggao Liu, which is from the Texas A&M High Performance Computing Center. So we were working as a group, as a core PI group, to develop training materials to help to broadening adoption of cyber infrastructure for disaster management. And we have over 10 different organizations, not only from the United States, also from abroad. For example, we have a National Land Survey of Finland, we have ADO, and we have UCL, I have Oxford University. We are developing an international training for disaster management network to help to train students, educators, and scientists to use CI and geospatial data science to monitor and manage disaster events. So for this project, we have 4 training modules. The CI-enabled computing module, we will teach how to access the CI platform, for example, the NSF Access. And we'll teach you how to use GPU, CUDA, how to write Python code. And for the geospatial analytics module, we're gonna teach students how to do network analysis, geosimulation, terrain analysis, and cyber GIS, social sensing, and GeoAI. And for the disaster data module, we're going to talk about the FAIR principles and 3 V's and data processing and data visualization. And finally, we have a monthly webinar. You might have also received my invitation sometimes early. We have a monthly webinar that we invite disaster management professional to give a talk about their work. So the goal of this project is to create 15 2 hours of CI-enabled spatial data science lessons, covering the HPC training classes and geospatial technologies for disaster management. So we just completed our first training session at the AAG annual meeting. It was really successful, and I have learned a lot, and it was very nice workshop. And we will launch a license through our activities, including the webinars. We're gonna also have a 6 days long summer school, next summer, not this summer. Next summer gonna be at the Texas A&M, and then after next summer gonna be the year after gonna be at UIUC. And we will also have a training session at the conferences. So we want to develop a sustainable cyber training community, and by recruiting additional students, educators, instructors, and partners to adapt, disseminate, and contribute to our curriculum. So we do also provide seed grants and travel support. So this is our next opportunity. So we're gonna organize another cyber training workshop at the Natural Hazard Center annual meeting in Bloomfield, Colorado, July 14th. So it's gonna be 1 day training session. So if you're interested in applying for the travel grants, so please submit your application to this Google form. And if you don't need a travel grant, you're just interested in this work, you can also fill out this form, the second link. So I will add you to the mailing list, and we will inform you later when there are other activities. Okay, I think that's pretty, much about my my presentation. I hope I'm not over the time. So any questions?
Thank you, Jo. I think this was a great and informative talk.
Mm.
Thank you for sharing. So any questions for Jo? Feel free to raise your hands or speak up, or you can also add to the chat. So maybe while people are thinking about the question, I have one for you, Jo. You were speaking about the data from the the coastal community that you were collecting, and from the and that they had like a data set that you were trying to make it available. So one question I have for you is, are you thinking about having computation also available close to the data, and maybe um, make the data accessible to where the computation is? So maybe bringing the computation to data, or data to computation, wherever it fits. So you have any thoughts about that?
Yeah, thank you, Anand. That's a great question. Yeah, especially I like the word data to computation, computation to data. Yeah, so they need to be well integrated. And since I'm not the data producer, right? So I've been really partnered with the USGS and also NOAA and NASA. And I have actually, because of time issue, I did not really introduce another of my work on knowledge graph, semantic modeling part. But yeah, so I've been basically more like a partner with others, and then help them to provide them with a better models, language models, so they can improve their data sharing platform. And on the other hand, I think for the cyber training project, we partner with Design Safe. I don't know how many of you know Design Safe. It's another data sharing platform that you can just publish your data, but any type of, not only geospatial, but also social, survey-based, or any kind of data set. So I think for data sharing, partnership is really important, and the technology can always improve. Yeah, answer your question?
Yeah, that did. Thank you so much.
Mhm.
Carol, I see you on.
Yeah, may I ask a question? So I'm wondering whether you can maybe just briefly talk about what you do for reproducibility, or how do you can incorporate that into all the work, especially the computational work that you're doing, and what kind of help you might need if you need any.
Yeah, so reproducibility is now very important. And first of all, we need to have our code and data openly available for diverse communities. And especially, of course, in my lab, all the published work, and they are in our lab GitHub. And so people can just take our code and maybe modify and reuse the code. And also, I think that in order to promote this reproducibility, we have to also think about the explainability, especially for the GLAI models, how to help the communities understand your code, right? And especially for disaster management, now so many communities, they really trust the model that people has developed. I think those are the two important parts. And also, I think for the cyber training projects, we are working on Jupyter Notebook. So we will, that's the Jupyter lab. So we use Jupyter Lab. So we're gonna share this notebook with the diverse communities so they can just run notebook and immediately see what's the outcome of the results. And we are trying to use the national recognized CI platforms. So for example, NSF Access, NSF Access is like a big umbrella that connect to many supercomputing centers. So for the cyber training projects, so the user can actually log in through NSF Access, and it's free of charge if you are the I think if you are at US. And so trying to use open accessible CI platforms and make code and data available to communities, and also try to maybe partner with the communities to spread the word about our work. So I think this probably are the key core elements for advancing the reproducibility of the data and the code.
Thank you. Thank you.
Hi, Dr. Zhang.
Hello.
Very interesting talk. So I have a small question towards the flooding level measure. Your study, using the photo and a stop sign. So I'm wondering, after you're building the model and measure the height from the photo, do you have any other data for validation or other methods for the validation to estimate how well the measurement taken from the photo?
Oh, that's very good point. Because we use stop signs because there's no data, right? So there's no ground truth. There's no data. Of course, we have hydrological models, and those hydrological models normally work well with the rural area. It doesn't work in the urban area. And the gauge data is very limited. There's many places there's no gauge. So I think you cannot get both. So if you if your goal is to find fine spatial scale data, then it means that there's no data available at that point. But we should think about that. That's really a great point.
Thank you.
Hi, Xiaowen.
Hi, Joe. Thanks very much for your nice and comprehensive sharing. Maybe just a comment you might already be aware of as you are creating these nice resources, and some of which are related to education and training. I think iGuide might be positioned to help you to amplify your impact from the resources either you have created or you will create in the future by helping get your resources better shared, or this could include the notebooks or data sets or some open educational resources. So think of those areas as potential leverage iGuide could potentially contribute to for amplifying the impact of your nice work.
Thank you. Of course, yeah, I will work with you and iGuide to make this happen. And also, I think cyber training is also a step of going to that direction. Thank you. Any other questions?
I actually have a dumb question. When I was looking at the final slide you showed, there was a stop sign. I was wondering whether that was a real stop sign buried by water or is a Photoshop stop sign.
It's photoshopped. Yeah, it's too big. It's not in the US standard.
Thank you. Yeah, I was so curious because you know, these days you could even use generative AI to create these kinds of images. The kind of the scale, the houses together with the water did not seem to be compatible to me. So I was curious about the authenticity of the stop.
Yeah. All right. Any other questions?
So hearing none, I think first of all, I would say thank you to Joe for taking time to sharing. I guess have a good sharing. I guess you had a very much covered a broad aspects of your research as well as teaching. So thank you for doing that. And as Chauvin said, we look forward to collaborating with you and integrating some of the things that you have to amplify the impacts of your work. So thank you, Joe, for doing that, and for all others. So we have this VCO series, which is happening every 2 weeks, roughly. So next VCO is on the 22nd, and you would hear a very interesting topic by Dr. Forrest. So thank you for that, and watch out for our information coming via various channels and social media as well. So look forward to hearing more from my guide and participating in our events.
Thank you.
Thank
Thank you. Thank you
Thank
for having me here, and thank you for all the opportunities. And and thank you for everyone for attending my presentation.
Thank you.
Thank you.
See you all in 2 weeks.
Mhm.
Bye.
Thanks.